Are you worried about losing power from storms or in the new ever-prevalent rolling blackouts people are experiencing around the world? Do you want to have confidence that critical circuits like your fridge, sump pump, microwave, internet, and security systems will still be operational in a power outage? Not for just hours, but for days. Do you want to be able to weather a hurricane without all your food going bad, or go on vacation without worrying about returning to a flooded basement? Well, the solution I'm installing in my house today can do all of these things for you, with or without solar. You can sustain critical circuits with today's very simple installation. Welcome back to Projects with Everyday Dave. Follow along with me as I install this simple, reliable, automatic emergency home backup system. All right, let's do a quick overview of the materials that we need. We don't need very many. This is a very simple install. I'm going to use a 125 amp load center. This has several spaces, so I can put several circuits in it. In order to power this load center, I'll need a 50 amp breaker on each side. And in this case, I'm using a single pole because this is a 120 volt only system. You can do a split phase version. In that case, you would need double pole breakers and 6-3 to connect it. You'll need a couple breakers for the emergency circuits that you're going to do. Those may need to be arc fault if they're in the house, or if you're just relocating your existing breakers, you can use those. You need a grounding bar to go in the load center, stickers to meet any code requirements for labeling. I'm going to use 1/0 cable. That's a little overkill for this particular system, but I want to be able to upgrade later. And you can get it from Current Connected with the lugs already on, or you can get your own lugs to build your own cables. In that case, I recommend using a crimper like this one. This is a lower cost version than some of the ones that are out there, but it works really well. And you'll need a few tools, wire cutters and strippers, utility knife, things like that, that really help. And for the battery side, you'll need a fuse, in this case, a 125 amp fuse. You want to get some wire staples to hold your wire and cabling in place. And I'm going to add an outlet right under my inverter so that I'll have emergency power available in the garage. In this case, I'm going to use a 2-gang box with a ground fault 20 amp outlet and a regular 15 amp outlet, so I can plug plenty of things in. An outlet cover, a little bit of conduit, and a connector to connect that directly to the sub panel. I'll be using 2 of these 48 volt, 5.12 kilowatt hour SOK server rack batteries. And if you've been doing any research on server rack batteries, you already know these are the best ones out there. They have great support from Current Connected. They have very nice posts for the conductor connections, built-in circuit breakers, and a sophisticated BMS with access to the controls with a built-in screen. They have every standard communications port, and most importantly, they are built like a brick house with quality cells. The cells are housed in steel mounts, and all of the connections are bolted, allowing for individual cell maintenance. There are 2 main packs that are securely and individually mounted. Every connection is bolted, so each one of these cells can be removed and individually maintained. All the wiring is zip tied and securely managed. Everything is perfectly laid out. The BMS is securely mounted. It's a high quality bus bar for carrying the load. The only negative thing I see in here is this cable is a little bit too tight in this radius. There should be a little more strain relief there. Other than that, it is just beautifully assembled. This is the best choice in batteries if you don't want to have any problems. And I'll be using the Victron 48 volt Multiplus-II 3000 watt 120 volt inverter charger. The nice thing about getting it through Current Connected is they will pre-program it for you to meet the needs of your exact setup. The unit comes with a spec sheet with pre-programmed parameters, a simple mounting bracket, and a temperature sensor to connect to the batteries. This unit is very heavy due to the large transformer, which also makes it very good for inductive and surge loads. It can work completely off-grid on battery power only and take line-in, generator, or shore power and manage the current demand from those inputs. For instance, if you're using a small generator or plug your RV into a 20 amp plug, the controller can limit the input to 20 amps and use the batteries to boost the output an additional 25 amps to make 45 amps available to your devices. I can also add additional units to expand in the future, so it's a great choice for a low cost but totally functional starting point for home backup. I just painted a piece of plywood to hang all of my components on. You can also use a piece of cement board. It adds a little bit of extra fireproofing. Hanging the inverter is very simple. Just mount the bracket on the wall, hang the inverter on the bracket, make sure it's secure, and then shoot the screws through the corner mounts. There has to be 10 centimeters or 4 inches of clearance around the inverter for airflow to make sure everything stays nice and cool. All right, now with everything mounted, it's time to wire things up. Fortunately, I was really looking out for future Dave when I wired my sub panel here. You can see I gave myself a lot of extra length in the conductors by winding them back and forth in the bay because I wasn't sure if this was my final location for the sub panel or if I might want to move those circuits later. Fortunately, I was thinking out for future me, which I guess is present me, so thank you, past me. The way this is currently set up, I have my main load center with a 100 amp breaker that feeds this transfer switch. The transfer switch can only take power from line or generator. Then I have this cable here that runs to a generator plug outside the building, and that allows me to have all these critical circuits switch between line and generator. So now I want to eliminate the need of plugging in a generator all the time when the power goes out. And what if I'm not here when the power goes out? So I'm going to take some of the most critical circuits out of this sub panel and put them over into our UPS sub panel. Circuits like the refrigerator, security systems, internet, things like that. So the way it'll work, my most critical circuits will always have power, even if the power goes out. Then, if I want to run some of my larger circuits that require generator, I can simply switch over to generator power, and I will now be running these critical circuits off of the inverter and everything else in this panel off of the generator. And if the inverter needs to charge the batteries, it can also pull from the generator. Now, most likely you don't have all of this, so the simple solution for you is to just run your 50 amp breaker directly in your main panel over to the inverter, and then all your emergency circuits in your sub panel. So there are a lot of ways to configure this. The most critical thing, a sub panel with emergency circuits. So let's move our critical circuits from this sub panel over to this one. And fortunately, I'm testing the Victron 2000 watt solar generator right now, so I can just plug my refrigerator into that unit while I'm doing all my wiring and not have to worry about my food getting warm. That's convenient. Now this load center, like other load centers, is set up for split phase. But we're only going to use one leg for this activity. And later, if I expand, I can make it split phase. So for now, I'll just use this one leg in the panel, which means I can put 2 breakers on this line and 2 breakers on this line. Put my 50 amp breaker in the bottom. Okay, I've removed the panel. Now, one of the things that I like to do is label my actual conductors coming into my panels. So this first floor kitchen lights, look, there it is. First floor fridge. So I know exactly which wires, even without the labels on the front of the panel, I need to manage. These are the 2 breakers that I'm going to pull from this panel and move over to our new sub panel, and that will make room for our 50 amp breaker that's going to feed our inverter. So I'll pull those breakers and put in the 50 amp to replace it. Okay, we want to turn the power off. There we go. Now we can rearrange our circuits. First, I mount the ground bus bar in the box using the provided screws. For routing convenience, I just put it off to the neutral side. The first circuits I'm moving are conveniently located at the top of the sub panel. Since they're arc fault breakers, both line and neutral go to the breakers, so they're very easy to disconnect, and then I can just pull them out of the panel and get them out of the way. To remove the arc fault breakers, I just need to disconnect the independent neutral wire that's used to detect arc leakage, and then remount them in the panel. The arc fault breakers have their own independent neutral wire, so I connect that to the neutral bus first. I'm using the top 2 slots. That way it'll be a lot easier to feed power in from the bottom to the 50 amp breaker and to drop power down to my outlet directly out the bottom. I popped in a standard 50 amp single pole breaker that will be used to backfeed power into this sub panel, and a standard 20 amp single pole breaker that we'll use for our outlet box later on. Then I can feed the wires for my fridge and emergency circuit back into the new box. I can connect the ground to the ground bar, and then the neutral and hot wire both connect directly to the breaker. The inverter has a nice set of dust boots where the cables go in and out of the inverter. If you're using Romex like I am, you simply take a long bladed razor blade and cut off the bottom of the accordion to match the size of cable that you're pushing through it. Start with the small step and move your way up if you're not sure exactly where to cut it. If you're using conduit, you won't need these for those connections. The inverter has plastic clamps that hold the conductor in place. I have to remove the top portion of that, but remember to be careful with it. It is plastic, and if you put too much force on it, it will break. Be sure and pull at least 8 inches of your conductor through the port so that you have plenty of wire to work with, just in case you make a change later, and to make sure you have plenty of wire to work with to set the conductors properly in the clamp. It's critical that you strip the full 1 inch or 25.5 millimeters of insulation off the end of the wire. The first conductor to go in is the neutral. Make a 90-degree bend about 1.5 inches to 2 inches from the end of the conductor, and then another 90-degree bend about halfway down the cable, and that allows you to flex the stripped portion of the wire into the slot with plenty of movement in the wire so you can make sure it's completely seated. Use a thin blade screwdriver in the slot above to open up the spring, and that will allow you to seat the wire the rest of the way in. Pull the screwdriver out and give the conductor a firm tug to make sure it doesn't come out. In this case, you can see it comes out easily, and a good indication that it wasn't fully seated is you could still see some of the bare conductor. So I can push the screwdriver back in and make sure this time that it is fully seated. There's no conductor exposed. And now when I pull on it, I can pull on it as hard as I want to, and it won't come out. For ground in line 1, I follow the same steps, a 90-degree bend about 2 inches from the end of the conductor, and then a reverse bend halfway down the wire. Shove the screwdriver in, make sure it's seated all the way, and I didn't have any problems after that. It's very important to make sure the conductors are stripped and seated properly. If they aren't, you can have a high resistance connection that can result in heat and destruction of the mounts and your unit. Now I'll take this line out from the inverter and use it as an input to backfeed the 50 amp breaker in the bottom of my critical circuit subpanel. The neutral connects to the neutral bar, and then line 1 connects directly to the breaker. Once again, I make an accordion shape in my conductors, so I have a little extra length available in case I move the breaker or make some other change later. Then I'll use 6-gauge wire once again to connect from my AC source panel and the 50 amp breaker there to the input on the inverter. I'll take the same care on these conductors to strip 1 inch or 25.5 millimeters. Put 90 in, come partway down, put another bend, push the release, good and tight. Now that all the AC lines are secured in the inverter, I can move over to the other end and connect it to the 50 amp breaker. I relocated one of the other circuits so I could put the 50 amp breaker in the bottom of my source panel. Then I could simply connect the ground wire to the ground bar, the hot wire to the breaker, and the neutral wire to the neutral bar. There's only one hot wire to connect because this is a single pole connection. It occurred to me that my 12-gauge wires are actually coming out of the wall, and so to properly protect those, I should be using a piece of conduit. So let's go ahead and replace that. All right, that's better. The better choice here would have been to use conduit and THHN cable, but I'm just going to use some cable staples and secure these in place. I made a little platform for the outlet box that goes over the cable and holds it the right distance out from the box so that my conduit will connect directly up to it without any issues. This is a 20 amp circuit, so I'll just use a scrap piece of 12-gauge Romex, connect the hot wire directly to the circuit breaker, neutral to the neutral bus, and ground to the ground bus. I'm not going to spend a lot of detail on wiring outlets. I'm sure there's plenty of videos out there for that. But just a couple things to remember. I'm using a ground fault outlet. Since this is a garage space, the power has to come to the line inside of the ground fault outlet, and then the secondary outlet just comes off the load side. That way they'll both be ground fault protected. And most importantly, when you put the cover plate on, make sure all the screws are facing the same direction. All right, that pretty much does it for all the AC wiring. I can put the covers back on and make sure not to forget to label your breakers. All right, breakers are all in, cabinets closed. AC's done. Now we can start the DC. I only have 2 batteries and I don't want them to take up a lot of space in the room, so I'm going to put them flat against the wall. I have a couple of wood strips against the wall and on the floor to keep them spaced out, and then I'll just use some steel shelf brackets and that will hold them to the wall. Even though they're super heavy, if there was an earthquake or something, I wouldn't want them to fall over. So that'll be my mount system. Carry this one just the way it is to that corner and then one right next to it.
Because they're not light.
No. No, they are not. Perfect, thanks. Even though these units are very heavy, I just want to secure them to the wall with a couple of shelf brackets. Lay down. Stay. So because I have my batteries set tight against the wall, they're not in the perfect setup for a parallel connection. In the server rack setup, the positive posts are directly above each other, and so are the negative. You can just connect them straight up and down. But because I'm putting them against the wall, I need a little bit longer cable. And I'm using 1/0 cable, which will be plenty for this configuration. And I'm going to use 1/0 cable going up to the inverter as well. That's because if I want to upgrade later, I won't have to upgrade the cables. I'm just going to use some 5/16 lugs because that's what size is required for these posts. And of course, I've made sure that the breakers are off. We wouldn't want anything on while we are doing our layout. So I laid out my cable about where it goes with the lug connected to the post. Then I can use a marker to mark the exact length that I want the cable to be and where the insulation will need to be cut. So I can cut those two to length and make them up. I like to use my cable cutters to make a nice clean score around the insulation before I use the insulation removal tool. When starting a new cable, I always set the depth a little bit shallow and work my way up so that I cut through most of the insulation, but not all the way through because I don't want to cut any strands. Then I can just kind of bend and stretch the cable to break the rest of the insulation and it comes right off. I just use the table to index the lugs so that they're both facing the same way and mark it with a marker. So as I crimp it, I can make sure it doesn't rotate. I set my crimper to the appropriate depth for the gauge cable, and then all I have to do is slide it in and manually crimp it. I really like this crimper. It does a great job. I usually set it just a little bit tighter than the index, and it makes a really nice solid connection. It's pretty fast. I just slide my pieces on and set the crimp. Then I just trim a small piece of heat shrink tube, put it over the end, and heat it up with a heat gun. I like to use the kind with adhesive in it. It seals very tight, and I don't have to worry about corrosion due to moisture. Before connecting these batteries up, I'm going to make sure that the breakers are both off and the BMS is off. If the BMS is on, you can take a tiny screwdriver and press this reset button, press and hold until the lights blink and it will shut down. Now everything is completely off and I can make my connections. I'm going to start with my ground cable and leave the far terminal open since I will be connecting my batteries from the end posts. So I'll set that in there, and the first thing I'll do is get them roughly placed and finger tight. Make sure I'm happy with how it's all setting up. In the absence of a spec from SOK, I used 12 Newton meters or 100 inch-pounds as the setting for my torque wrench for the lugs, which is the same setting that Victron specifies for the connection to the inverter. All right, our parallel connections are securely made. Now we can make our series connections up to the inverter. The batteries are off, but the inverter is connected to AC and currently running. And I want to turn it off before I connect the batteries. And just to show you why you might want to do that, if I check the battery terminals here, you can see I have 55 volts available on those lines. And I wouldn't want that to be the case when I'm connecting things up. So we'll just go ahead and shut it off. Now it's off, and just to be sure, I can turn off the breaker. All right. Now I'm still showing a voltage, it's 43, 42, and that's the capacitors that are slowly draining down. So pretty soon that'll be zero. I've pre-made the cables for these connections. I have my fuse block, a small connector for that, and my positive and negative cables to go down to the battery. And I've already cut the dust grommets to fit on them, so let's connect it up. Negative cable first. The torque setting in the Victron manual is 12 Newton meters, which is about 100 inch-pounds. All right, there's the negative. And in absence of a torque value for SOK, I'll just use the same one as the Victron connection, 12 Newton meters. For the positive cable, I start with a very short piece because I'm going to connect the other end to the fuse holder. After it's torqued down, I can then slide the fuse holder on the end and clamp each end of the fuse holder and screw it in place. The fuse holder has to be screwed in place before the bottom cable is put in, or there's no access to the screw. After connecting the positive cable, I use some mountable zip ties to secure the rest of the cable to the wall. The Victron inverter requires a 125 amp fuse. Now, we only have 2 batteries. However, because they're combined in parallel, they can provide over 200 amps. And the Multiplus-II requires a 125 amp limit. Now, if I had a very large battery bank, I would probably use a Class T fuse, but for just these 2 batteries, we can use this CNN 125 amp fuse. Now, you can't use an ANL fuse because they can't handle the voltage, but the CNN fuse can handle up to 80 volts. There's a series of plugs in the middle of the wiring bay, and the temperature and voltage sensors are the back plug. Just pull it out. The temperature sensor is the left side 2 connections, and make sure and note that the far left connection is the positive. To make sure I don't confuse the positive and negative for the temperature sensor, I'll just take a Sharpie and mark a red plus sign for the positive wire where the temperature sensor goes in. Then I can simply insert the plus and minus wires into the plug and tighten them down. Then the other end connects to the negative terminal on the battery. I'm just going to use an open negative terminal for convenience. The internal bus bar will directly connect them, and they should be pretty much the same temperature all the time. Slide the dust boot on and put a regular bolt in, and then torque it down and recover with the dust boot. And now I can plug it into the inverter. Try not to forget to slide the dust boot on the wire before you connect the plug to it, like I did. After that, it's pretty easy. Just pop it through the hole, plug it in. Then I just zip tied it to the main cables all the way down to the connection point on the battery, and the temperature sensor's done. Now, if you're using large cables like the 1/0 cables that I'm using here, the dust boots that come with the SOK battery won't fit over them. However, if you just take a pair of scissors and cut through the boot, it'll open up and you can just slide it right over, even with larger terminals. Then if you want to secure it there, put a little zip tie around it. There you go, dust boot. Now all the terminals are covered. I don't have to worry about accidental contact across any of the posts, and we're good to go. All right, now with everything off and all the wires connected, we're ready to start up our batteries. The startup procedure for these batteries is very important. If you do it the wrong way, you can damage them, and that's not covered by warranty. These batteries have a very sophisticated BMS with a pre-charge resistor built into it. Large inverters have large capacitors that require a tremendous amount of current when they're initially connected. That can damage the unit. The pre-charge resistor in these units will slowly charge those capacitors, preventing a large inrush of current. Now I've connected my clamp meter here set to inrush so I can measure the actual inrush, and we'll see what the impact of that is. Before we start, make sure that the batteries are completely off. The breaker is off and the BMS is off. If the BMS is not off, use a small screwdriver and press the RST button for a few seconds. You'll see the lights blink and it will shut down. The proper startup procedure is to turn the breakers on for every battery, and then we'll press the RST button for the primary battery. In this case, it doesn't matter which one we use, but we'll call this the primary battery. So I'll press and hold the button. 1, 2, 3, the lights come on, battery kicks on. The other battery automatically comes on with it. And we had 19 amps for our inrush current, which is nice and low. When I was doing my 12-volt battery setup, I was getting inrush currents of 130 to 230 amps, depending on the inverter. So 19 amps, that's really good. Now that our batteries are turned on, we can turn on the breaker for the AC and the switch for the inverter. Power to the inverter, and now I'll turn on the inverter to position 1. Inverter clicks on, we'll give it a few seconds, it'll recognize the mains, and then we'll see how much current it sends to the batteries. I can hear the inverter powering up. Let's check the, so we're putting 34, almost 35 amps into the batteries. So each battery would be about half that. Oops. Yep. 18.5 amps. And I can check on the BMS. It's showing 16 plus amps going into the battery, 53.8 volts and climbing. Now if I check the AC current, looks like I've got 18 amps coming in, charging the batteries and running other devices. The other devices must not be drawing much. Yeah, it looks like half an amp going to outside circuits. There it is, all powered up and running. I'll let the batteries charge up and then we'll do some load tests. All right, it took about 3 hours to get the batteries fully charged. Now that everything's fully charged and ready to go, I'm going to simulate a power outage and we'll see how long my fridge can run on just these batteries. And lights out. Switch to inverter on. Drawing a couple amps from the batteries. Looks like we're drawing just over an amp from each battery, so the fridge is definitely running. So far the fridge has consumed 0.19 kilowatt hours. We're running at exactly 60 hertz. It's pretty impressive. The watts is 106 right now, 0.93 amps, and 118.6 volts. Obviously supplying it perfectly without even breaking a sweat. Batteries are supplying the power. Let's see how many days it can run. This is by far the longest fridge test I've run yet, but it's kind of boring because nothing happens for days. But the test finally finished and here's the results. So the fridge hit just under 100 hours, truly long-term reliable performance. The orange line shows the battery capacity starting at 100% and dropping down to 0, and the blue line is the kilowatt hours consumed by the fridge. So on day 1, we dropped the battery down to 75% and the fridge used 2.38 kilowatt hours. And then after 48 hours on day 2, we had 52% battery life left and the fridge had consumed 4.4 kilowatt hours. Day 3, 72 hours later, the fridge had consumed 6.58 kilowatt hours and the battery was down to 28.4%. And then finally on day 4, after 96 hours of use, the fridge had consumed 8.59 kilowatt hours and the battery was down to just under 6%. And then a few hours later it dropped off and we achieved 8.73 kilowatt hours of total consumption by the fridge before the battery hit 0%. All right, let's pull all that together. The fridge's average daily consumption was 2.13 kilowatt hours. And for 4 days, it took 8.59 kilowatt hours. And the total power consumed for the 99, almost 100-hour runtime was 8.73 kilowatt hours. The two batteries combined is 10.49 kilowatt hours. And since we used 100% of that, by dividing those two, we get a total overall efficiency of 83.2%. Now, since this is a low-frequency inverter, that's pretty good, considering that there's always some standby consumption over that 4-day period. And now if I want to add additional loads, I can use that 83% efficiency to determine how many batteries I would need to achieve it. All right, I have a lamp here, so I can check the UPS functionality. All I have to do is turn the breaker off and we'll see if the lamp stays on. All right, shutting power off. Switched right over. Not even a flicker. Inverter's running. Mains are off. Power's on. Awesome. Now I want to do some other testing. I've run a very long extension cord to my shop. And now we're running off the batteries. I want to see what kind of tools I can run off the 3000 watt inverter. Now the Victron has a large toroidal transformer, so it should be able to handle those inductive loads really well. So let's do some testing. Okay, I'm going to put my clamp meter on the batteries so I can see how much current I'm drawing from the battery while I'm cutting in the shop. I'm already drawing 0.2 amps here because I have other things running off the inverter like the fridge and stuff, but mostly it'll be the chop saw. All right, we're at the other end. This is a very long extension cord, so we'll probably see a little bit of voltage drop over that distance. And 119.5, that's pretty good. All right, let's run some tests. We're only pulling 41 amps from the SOK batteries. That's the huge advantage of having a 50-volt battery pack. When I was using the 12-volt setup, I was pulling 180 amps to run this saw. That was fantastic. I couldn't even tell I was on the inverter. That cut just like it would have cut if I was on regular power. It's coming in right at 120 volts. Didn't even hesitate. That was fantastic. We better try some bigger loads, I guess. All right, let's try a planer. This is the most difficult tool I have to run, and it regularly trips the 20 amp breaker. I have a helical head in it, which uses a lot more power than straight knives. I have a very hard slab of yellow locust, and it's curved at the top, so I can take passes and work my way down, and it'll just get harder and harder to run. And I've attached my clamp meter and a voltage meter, so I can monitor how much power is getting consumed as I run the different runs. So let's power it up and see what it can do. Man, I love it when things actually work. I can hardly stop smiling. That was so awesome. I was drawing more than 30 amps. That's nearly 3,400 watts that I was pulling out of that system, and it didn't seem to care. The batteries, of course, weren't even being taxed, but the inverter, that's over its capacity. I couldn't draw any more than that. The planer was bogging down, and its internal relay would have tripped if I had pushed it any more. But man, what a great result. If it can run this piece of equipment, it can run anything in my house and probably anything in yours. And of course I have links to the battery, the inverter, and other key components that you might need to do an install like this for you. It's all in the description below, so be sure and check that out. Using those links helps out the channel and helps me bring more really awesome content like this. If you haven't seen the new array I put on my shed, I'll put a link to it right here. Check it out. It's pretty neat, and it's really adding a lot of power to my total system. I have a SunGold inverter, an EG4 inverter, a SolarArc 15K we're going to do some investigations with. I have some bifacial Q cells I'm going to compare to the Canadian solar bifacials that I have. All kinds of really neat content coming up, so be sure and subscribe, and I'll see you next time.